So, good afternoon, everyone. Today, this is the seventh session of problem solving in the course of Computer Engineering Thermodynamics. The instructor is Shashidhar Gumasa from IIT Tirupati, and I'm Namrata Kulkarni from IIT Madras. So, till now, till week 6th, we have discussed about properties, physical properties like enthalpy, temperature, like energy properties like internal energy, enthalpy, Gibbs energy, and Helmholtz energy, like these, and how to find out them for single phase systems. And we have also discussed about residual properties because we can't measure the actual properties. We use residual properties, which are expressed in terms of temperature and pressure. So today we are going to discuss solution thermodynamics. So I hope you people have all gone through the video lectures uploaded in online by Guma sir. So I'll be dealing with the summary of the sessions and also a few problems to get a idea, clarity to how to solve things. So we'll just take a few questions today and impress more on how to solve them instead of solving so many problems. Okay. So till now we have seen that and properties of a system are dependent mostly on the measurable properties like temperature and pressure. But when it is a two-phase system or multi-phase system, like gas mixtures or liquid solutions, composition of the system like X1, X2, which are like molar fraction of the system, are also essential here, along with the temperature and pressure. So initially, we know these fundamental properties, property relations, right, for a closed system. dNu is equal to TdNs minus PdNv for UHAG. Sorry, this is A, right? So, but now, if I'm considering a two-phase system where this is liquid and this is gas, then it is an open system. For example, this phase is an open phase. Like components can be exchanged between the two phases. So it is open for a single phase, right? The whole thing can be a closed system, but among themselves, the components can be exchanged. So that's why the properties of this liquid phase, for example, this is alpha phase and beta phase, not just limiting to the liquid and gas. We can also say that this is one liquid phase, alpha, and one gas phase, sorry, liquid phase only, beta, right? So that's why the properties of this G alpha, G beta, so like these are functions of just a minute. Net problem is there. That's why I'm switching off the video. Are not only function of T and P, but now they are function of T, P, and Xi or Ni. Okay, and if we differentiate it like total differential, then it is obtained as dou Mg by dou P, T comma N. That means this is at constant temperature and number of moles, all the number of moles into dP, and similarly for temperature, and this is for moles. Okay, this will be sigma of, like, I have two species as you, then by dou N1 into dN1 plus by dou N2 into dN2. So summation of things will be there. So here, what is there? Dou Ng by dou Ni. at constant pressure and temperature and other moles of other species, other components, then it will be mu I. This is named as chemical potential. Okay. So here we can see on comparison with this and this here. So we already know this NS is this one. So we already know that dou of Ng with respect to dou T at constant P equal to minus Ns, right? And here, sorry, not T, and this is P. Okay, so we know that this term is minus Ns. And similarly, this NB is given for this. So NVdP minus NSdT plus this is mu I, right? So sigma of mu I into dni. So this is there. So we have these relations. Where this is equation 1. One more equation is, I'm assuming Nj also here. And everything, okay, and everything. And also dou Ng by dou P at constant P and N is equal to NV. And this is equation 2. So we have got relation for S and V. And now we have relation for G also. And H we can get from G plus TS. Right? So like this is DS. Sorry. Yeah, okay. When you have a relation for G already, so you get what is S also, what is V, and also H, which is defined as G plus PS. So the if we have a relation for G, then we'll have the complete property information. Okay. So that's how. So here, yeah. Right. So, how I said is this is liquid phase alpha, not liquid only, alpha and beta phase. Okay. So one more thing I want to say here, if it is a one phase system, or two phase system, and it is a closed, then again the initial equations which we have defined dg d of ng is equal to this one minus NSDT plus NVDP. So this is followed already. And also this equation dNg is equal to minus NSDT plus NVDP plus mu I dNA is also followed. So that and this both are followed. It implies that the sigma of mu I dNi is 0 for a closed system. So this is, I'm talking for the whole system if you consider this is followed. And even if it's a single phase, that is followed. That's why we have removed that term, and only this term is expressed for the single phase system, right? And when we come to individual phases, the same relation can be expressed as dNg for alpha phase, okay, and also for beta phase. So now for the whole system, it can be expressed as summation of these, okay, right? Because these are like extensive properties which are based on the mass of the system, like whatever is there. So energy properties are like summation is understandable, right? So that's why we sum up the nm of alpha and beta. Here m is extensive property and molar property. Okay, molar means per mole. So that's why we multiply it with n. So when we check out this, so similarly for the alpha and beta, if we sum up, this is NB, right? That's why we get the summation of these things. And as we know, for the whole system, this summation is 0. So summation of these should be 0 here at for the whole system. And also when this is equilibrium, right, at the equilibrium, this becomes 0. So this is given as d of NG, right? That's why this is 0. And we know one more thing is that because the both phases exchange materials, so whatever number of moles are lost by this phase is equal to whatever number of moles are gained by this phase. This one. Okay. Of the each species also, okay, different components also. It's not like uh, total number of moles are conserved or something, okay. In this, I'm not saying that in this phase completely only 50 moles are there, okay. To attain equilibrium, they are exchanging things. So for a given temperature and pressure, generally, if I'm talking about like water and water vapor, okay, liquid water and vapor. Then at each equilibrium, there will be some humidity in the air, right? So similar to that, there will be some water in the air and completely water in the liquid mixture. There can be some air inside the liquid also. So that's why we have x1, x2 and y1, y2. Okay. Now, if I change some temperature or pressure, okay, then the new equilibrium point has to be attained. So then what happens? Just a small exchange of mass happens here to attain the new equilibrium. So here, I'm only talking about two species. Okay, so if 50 moles of phase of liquid phase is there, and out of that for example, 5 moles of air and 45 moles of water is there. And in this, for example, 40 moles of air and 10 moles of water is there. Okay, so out of 5 moles, maybe this time 2 moles will go. So of course, this will gain 2 moles of air, 40 plus 2. And out of 10, maybe 3 moles of water will come down. So plus 3, right? So how many moles of each phase are there now? minus 2. 3 plus 48. 51. And here 42 plus 7. So 49. Overall moles of the system are conserved, but it's not necessary that number of moles in each phase has to be conserved. But the transfer of specific component or species in a phase, they are exchanging the same material. So that's why this is DNI alpha. The is same as like gain and lose, or the ulta also. That's why minus sign is used here. So considering that in the above equation, which is this one, so considering that, we get sigma of mu I alpha minus mu I beta is into DNA alpha is 0. Assuming that there exists some finite transfer, so this is not equal to 0. So that's why this should be equal to 0. So that's why at equilibrium, mu I alpha is equal to mu I beta, which is like generally you say mechanical equilibrium. Okay, you say force 1 is equal to force 2. Right. Not pressures. Please note that is force balance we do. And heat equilibrium, thermal equilibrium, if we say, we do T1 equals to T2. Similarly, when it comes to chemical equilibrium, it is mu1 is equal to mu2. Okay, it's not concentrations equal, its chemical equilibrium is potentials are equal. Okay. Now, and how is chemical potential defined as dou Ng by dou Ni? At P, T, Nz. Mu1 alpha, mu1 beta, okay, or else mu I1. I'm just correcting the above statement, that's all. Okay, so P and T and Nj. So that's what we mean here is at constant pressure and temperature, this mu is defined, right? So like at an equilibrium, we are defining it. So that's why the statement is given as thus multiple phases at the same temperature and pressure are in equilibrium when the chemical potential of each species is the same in all phases. So this is what we have learned till now. What is the fundamental property relation for an open system? How is it changed? And then what is the definition of chemical potential? And how is a chemical equilibrium defined? Now, as I said earlier, the total properties are obtained when we have models for the G and this mu I also. Dou Ng by dou Ni. So when we have G, then we have relation for mu I also at constant pressure and temperature, right? So that's how we will obtain every fundamental energy properties. Now we define partial properties, which is Mi bar is equal to dou Nm by dou Ni Pt and J. So this mu I is actually equal to dou Ng by dou Ni, right? So M is G here. So Gi bar is mu I. So this is defined as partial property. The total derivative term will have these partial property things. So when we say there are three different kinds of properties defined, solution properties. So in a system, 1, 2, 3, so on, number of species are there. Okay, NS. And each will have some MI. Okay, each species has their own energy, their own volume, internal energy, right? Entropy and all they have. For example, okay, we'll go by understanding the volume of the system. Okay, so volume of each species is there, and partial properties is dou this one dou m n into m for the whole system is this one, right? Dou m by dou ni n1 or n2 whatever at pt and nj, that is defined as mi bar, and this is m. So in the video classes you have been like it is all this has been derived, right? And we get that m is equal to sigma xi mi bar. And so how do we get this? There was a relation where ni plus something into dni equals to 0. Okay. So from this, we get this one, and from this, we get this one. So m is equal to sigma xi mi is there, and also we get dou m by dou p, dou m by dou t minus xi dm by bar. And for constant p and t, this dou p is going to 0 and dou t is going to 0. So that's why this term equivalent to 0. So that is Gibbs Duhem equation. So we have obtained what are the relations for each thing. So now coming to that from the earlier slide, we have got that m is equal to sigma xi mi bar, right? So from that we have this, and also if we differentiate this, we get this thing, and we already know dni is equal to minus of dA nj, so that's why on derivation and all on substituting this inside this and later substituting into this equation, we get dm by dx1 is equal to m1 bar minus m2 bar. So final derivation gets us these equations. And for the binary thing, we have the summation as x1 dm1 bar by dx1 plus x2 dm2 bar by x1. So what I'm saying is, if I have an expression for m, I can get expression for m1 bar and also expression for m2 bar. From that, I can further differentiate this dm1 bar by dx1 and also dm2 bar by dx1. Then the summation will be coming as 0. So if I don't know the composition source, I can find out in that way. So coming to first problem, the need arises in a laboratory for 2000 centimeter cube of an antifreeze solution consisting of 30% methanol in water. So if it's like mass fraction or volume fractions kind of thing, generally it is mentioned there itself. Generally it is mentioned 30% mole, 30 mole percent, okay. Generally 30% if it mentioned also, then you can consider that as mole percent, okay. When you buy chemicals and all, so it will be mentioned easily that this is 90%, this much, 10% is right like that. So here it is explicitly mentioned mole percent, but generally 30% if it's given without any mentioning, then it is mole percentage. So x1 is equal to 0.3 and x2 is equal to 0.7. What volumes of pure methanol and pure water must be mixed to form the 2000 centimeter cube? So what we have is V. Okay, V is 2000. And we want to know V1, V2 to be added. So partial molar volumes for methanol and water are already given. Okay. So what we have now, we have V1 bar and V2 bar, right? We don't know completely how many moles of species are there. So firstly, I have a relation that V is equal to N1, sorry, X1 V1 bar plus X2 V2 bar, right? So if it is 1 mole, so in 1 mole you will have 0.3 into V1 bar, that 38.632 plus 0.7 into V2 bar, 17.765. Okay, and this gives us 24.025 centimeter cube per mole. Right, this V is a molar property here. So total volume we have Vt is equal to N, total number of moles into P. It implies Nt is Vt by V, which is 2000 by 24. It is given as 83.2 moles. And already we know mole fractions, right? So based on that, we have N1 also. N1 is equal to 0.3 into N, right? So that's why it is 24.97 here, and N2 is 0.7 into N. So it is 58.2. And summation gives you this one. Now, what is the total volume of each species in the added mixture? V1 total is equal to N1 into V1. This Mi. Okay. And this is given as 1017 centimeter cube. And similarly, V2 total is 1053 centimeter cube. So what you have to notice, one thing you have to notice is generally volume of added thing is 1017 centimeter cube. Okay, first species, and 1053 of second species was added together, but final thing volume is 2000, which is actually less than the summation of these. So it is not V1 total plus V2 total, but instead it is x1 into v1 bar plus x2 into v2 bar. So this n1 v1, whatever v1 total is there, by changing by adding it into one more solution, right, into a mixture, its volume changes. It decreases or increases. These all depends on the combination of the species, right? So all that will be discussed later, where different types of combinations are there and how will the properties change. So similarly for the, so this here we have discussed the volume thing. So similarly, it is easy to understand, okay? When you add two components, it is not necessary that the final volume should be the summation of those volumes. Rather, it is decreased here because of the interaction. So maybe these two species attract each other. So that's why the whole phase volume has decreased here. If they are repelling each other, the total volume after mixing will be more. So in the next week, the mixing properties will be discussed. Coming to the second question, the enthalpy of a binary liquid system of species 1 and 2 at fixed temperature and pressure is presented by the equation. Okay, this is in terms of x1 and x2. So find expressions h1 bar and h2 bar. So we had this m1 bar and m2 bar. So here we have to find the dou dm by dx1. So first addressing the first question, determine expression for h1 bar and h2 bar. So I'm h itself, I want to write in terms of only x1 because I want dh by dx1, the total derivative. So I'm writing this. Here we know x1 plus x2 is equal to 1, right? Mole fraction. So that's why I have 400 x1 plus 600 1 minus x1 plus x1 into 1 minus x1 into 40 x1 plus 20 minus 20 x1. Okay, and this turns 400 minus 600, so minus 200 x1. And here plus 600 plus here x1 is there, minus x1 square is also there, right? X1 into this is 40 minus 20, 20 x1 plus 20 minus x1 square, 20 x1 minus 20. So we get minus 200 plus 20 minus 180 x1 and the 600 and this 20 x1 square and minus 20 x1 plus 20 x1 square. Okay. Yeah. So sorry for the distraction. Right. Okay, one get 20 x1 cube. Right. So we have dh by dx1 equals to minus 180 and minus 60 x1 square. So h1 bar is equal to h plus x2 dh by dx1, which gives us h, which is 600 minus 180 x1 minus 20 x1 cube plus x2. So 1 minus x1 into minus 180 minus 60 x1 square. So upon solving this, you will get h1 bar equals to 600. Okay. 420 minus 60 x1 square plus 40 x1 cube. And similarly, you will get h2 bar is equal to 600 plus 40 x1 cube. So this is how we have got relations for h1 bar and h2 bar. So our first objective has been done as a functions of x1. So we have done. So numerical values for the pure species enthalpies h1 and h2, and numerical values for the partial enthalpies at infinite dilution h1 infinity and h2 infinity. So generally h is given as a function of x1 and x2, right? So h1 is equal to h at x1 is equal to 1, right? and h2 is equal to h at x2 is equal to 1. So if you see that, then we have got this, yeah. Here x1 1 and x2 0, right? So this term goes. So h1 is 400 and h2 is 600. And this shows the interaction term x1 x2 40x plus 1 plus 20x2. So this is 400 and 600. And this is in joule per mole. So these are molar properties that you know already, right? So next thing what we want to know is H1 bar at infinite dilution and H2 bar at infinite dilution. So this is when H1 bar is at x1 is equal to 0. Means tends to 0, infinite dilution, right? And x2 is equal to 1. This is H2 bar when x1 equal to 1 and x2 tends to 0. So this is given as h1 bar, which is this. And we have x1 0, 420 plus 40, 460. Oh, sorry, this is x1, right? So this is also 0. So 420 only. And this is 640. So x1 equal to 1, right? So 600 plus 40. 640. Right? So we know how to find, given a relation for m, we know mi bar how to find in case of binary solutions. We have derived given an mi bar and mi equals to m at xi equal to 1. And later mi bar at infinite dilution also we know how to find. So final question we have. At constant temperature and pressure, the molar density of a binary mixture is given by rho is equal to 1 plus x2. So the thing is, we have to find V1 bar infinity. So V1 bar infinity is equal to V1 bar at x1 equal to 1. No, sorry, 0. Okay, this is a binary mixture. That's why I am following the same, and x2 is equal to 1. So I need to know what is V1 bar for this. So first I need to know what is V, right? So rho is equal to 1 by V. Therefore, V is equal to 1 by 1 plus x2. And V1 bar equal to V1 plus x2 dV by dx1. Okay, so if I'm putting x1, I'll just write it in terms of 1 x1, okay? 1 plus 1 minus x2 x1, right? So it's 2 minus x1. So this is 1 by 2 minus x1 plus 1 minus x1 into. So differentiation of this with respect to x1 is, first I'll differentiate this, okay? Some, for example, 1 by some variable, 1 by u, then 1 minus 1 by u square, right? So 2 minus x1 square into du by dx1. So du by dx1 is minus 1. So this gives us 1 by 2 minus x1 plus 1 minus x1 by 2 minus x1 whole square. And at infinite dilution, x1 is 0, therefore 1 by 2 plus 1 by 2 square equal to 3 by 4. So this one. So I think everything is clear how to find, and given an m, we get mi bar, mi and mi infinite dilution. And we also have gone through how these expressions have been derived and why they have been derived. Like every term has a physical meaning. Right. So that's all for today. Next time we'll be coming with mixing properties and ideal gas relation for the molar properties. So thank you for today.